Hi there, and thank you for watching my video on data transformation and assessing basic assumptions in linear regression models. So imagine that you have a scatter plot and you do not always observe a linear relationship. So how can you transform your data in order to still use a linear regression model? And also how to check the linearity assumption, how to check the homoscedasticity assumption, how to check the normality assumption. This is what I will answer in this short video. I will also show how to use simple graphical tools using Excel. So let's get to work.
Imagine that you have a scatter plot and you would like to fit a regression line to the scatter plot. And imagine that part of the data contradicts your theory, your nice linear relationship. You may be tempted eliminating that part of the data to force the linear relationship, but this may have dramatic effects. Let me show you what can happen if you eliminate data.
SRB hydraulic power units have started. T-minus 21 seconds, and the solid rocket booster engine gimbal now underway. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Control program. Roger, roll, Challenger. Good roll program confirmed. Challenger now heading down range. Engines beginning throttling down now at 94%. Normal throttles for most of the flight, 104%. We'll throttle down to 65% shortly. Engines at 65%, 3 engines running normally, 3 good fuel cells, 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles, downrange distance 3 nautical miles.
So the 25th Space Shuttle mission is now on the way after more delays than NASA cares to count. This morning it looked as though they were not going to be able to get off.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
Looks like a couple of the solid rocket boosters blew away from the side of the shuttle in an explosion.
Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
So what happened and how is it related to eliminating data? Now, the sad part was that there were 7 crew members who died in this explosion, including a woman who was a school teacher, and she was one of the thousands of applicants for this flight. She was supposed to give a live lecture out of the space. Now, this was the famous Challenger disaster that happened on January 28, 1986, and well, the night before the flight, NASA held a meeting, a 3-hour meeting. They knew that it was dangerous to launch the flight, but they held a meeting precisely about whether launching or not the flight. Now, the reason of the meeting was that the predicted temperature was 31 Fahrenheit. For the moment of the flight, and NASA knew that low temperatures were dangerous for launching the flight. They even knew which part of the space shuttle was sensitive to low temperature. precisely it was the O-rings. What are the O-rings? So if you look at the space shuttle, so this is the orbiter, this is where the 7 crew members were, and at the launch, the orbiter is launched with the external tank and 2 solid rocket boosters together. And well, after 1 minute, all this is supposed to separate from the orbiter, like they did, but they are not supposed to explode. So, where are the O-rings? Well, if you look at the solid rocket boosters, you see these are joints. You have actually 6 such joints, and if you magnify these joints, then this is one joint. Then you see that the 2 parts, like the upper part and the lower parts, are joined together with 2 so-called O-rings. Here, these are the O-rings. These tiny, what you can see with black boxes. And what happened is that these were sensitive to low temperatures. NASA knew it because after each launch, they had 24 safe, successful flights before this Challenger disaster. After each flight, each launch, they recovered the rocket booster, solid rocket boosters from the ocean, and they counted the number of O-rings that were damaged. And so, for security reasons, they actually had 2 O-rings, one below the other one. In case one breaks, there is still the other one that holds. If 2 on the same joint break, well, this leads to an explosion, which is what happened during this disaster. Now, during the 3-hour meeting that NASA held the previous night, the night before launching the flight, they looked at a scatter plot. They looked at the number of incidents with O-rings for the 24 previous flights and the temperature in Fahrenheit at the launch. And what they did is that, okay, they did a simple linear regression, right? They drew a line going through this scatter plot, and the predicted temperature was 31 Fahrenheit, which is somewhere here. If you look at the prediction with this linear prediction, well, you see that it was already kind of dangerous to launch the flight, but so predicted number of damaged O-rings would have been something like 3 or 4, right, at this low temperature. But well, what happened is that, well, if the 4 incidents happen on 4 separate joints, it's not catastrophic, but it was still kind of dangerous, right, to launch the flight. But with some chance, they could have saved this disaster. Now, the situation was actually even worse because they did not report, they actually deleted the 0 incidence cases. So they should have looked at this scatter plot. So here you see that the zeros, all those cases where the number of incidents is 0 with the O-rings, happened in high temperatures, right? And if you look at this plot, you immediately see that it's not the linear relationship that you should fit here, but a non-linear one, right? Something going like this. And if you fit a non-linear relationship like this, you immediately see that at 31 degree Fahrenheit, it's not just 4 O-rings that are gone, but all your O-rings are gone, right? Which is what happened during this launch. Now, well, enough talking about dramatic effects. Let's relax a little bit and take an example from golf. Now, I don't know whether you know golf. I don't know much about golf, but what I understood is that you need to play 18 holes in the least number of strokes. And in this data set, which is posted on the course website, you have, let's open this data set. You see 22 golf players, and the scores are proportional to the number of strokes. So the smaller the score, the better the performance of the player, and the winnings in US dollars. Now, if if you draw a scatter plot, then this is what you see, right? And well, it's also a kind of a nonlinear relationship, but you can try to force a linear one, right? Nobody forbids us in doing so. And if we close our eyes, this is what we obtain when doing simple linear regression. How did I do it? Well, I simply regressed. Here, if I go back to my data set, I used data analysis, which is a free add-in in Excel. You just need to activate it, data analysis, and you select regression. And here in the input Y range, you enter your winnings in US dollars. And in the input X range, we enter the scores. Now, I have labels in my columns, and I would like to, for later use, I also want to have the residuals in my regression and the standardized residuals. And I would like the output to be displayed on this sheet. So I will enter this cell here. Here you go. I press OK, and this is what I get. Right? Now, I have a high R square, 61%. But the number of observations is 22, right? So it's always easier to get a high R square with the small number of observations. So this is what I obtained by using a simple linear regression. But actually, I noticed already that I have a nonlinear relationship. Now, let's try to fit I will report here a transformation. So if you see such a nonlinear relationship like here, then the first thing to do is to try some transformations, some data transformations. So here, since this is an inverse exponential relationship, I will do a log transformation of my y variables. No matter which base you take, I will take the log 10 basis of the winnings. So in Excel, you write log 10, and this is what I do. And now, if I regress the log winnings on the scores, I do not transform. I could transform also the score, but it should be enough in this example. Let's do a regression now of this time the log winnings. Here you go. Yes. And otherwise the X range is the same. And I would like the output to be displayed here. Here you go. Now, if we compare this R squared, the new R squared, this is when regressing the log winnings on the scores. We can also do here a scatter plot, just to check how does it look like. Let me just move this plot that kind of disturbs me here. I will put it here. I will do a scatter plot of the scores. And log in base 10 of the winnings. See, this time it looks much more linear than the previous, right? The previous scatter plot. So even if my relationship between the winnings and the score is a nonlinear one, by simply doing a transformation of my y variables, I managed to reach a linear relationship. And indeed, my R-square now moved from 61%, it jumped to 94%, right? And this is what I reported here, right? This is on the scores, and this is now on the log winnings, using the log winnings. Now, this is just one way of doing a transformation. Now, sometimes you need to try several transformations. Sometimes you also want to do a transformation of the x variables, and the higher the R-square, the better the linear relationship, right? So that's the goal. Each time, once you manage to, you try several transformations, and you take the relationship that provides you the highest R-square. Now, this is for the linearity assumption, basically. How to check other assumptions in a simple linear regression. And what do we have as assumptions? First of all, we assume that there is a linear relationship. We kind of know already how to check this linear relationship and how to remedy when there is a nonlinear relationship. But we have other assumptions in a regression model. We also have the fact that the epsilon size, the error terms, have the same variance, right? It's called homoscedasticity. And how to check whether this homoscedasticity holds. Also, we assume that the residuals, the epsilon, the error terms are independent. How to check whether this is actually a reasonable assumption. And finally, well, Galton said that the errors are follow a normal distribution. Now, is it satisfied in our data? We will also see how to check whether this assumption holds. Let's start with the linear assumption. We kind of know already when we have just one predictor, right? In the golf, in the winnings example of golf players, this is what we check. But sometimes we have more than one predictor, and simply a scatter plot is difficult to produce. So something that works even when you have several predictors is a diagnostic plot. And what is this diagnostic plot? You actually plot the residuals against the predicted values. So this is what I did here for the golf example. I plotted the residuals against the predicted values. Predicted winnings, concretely, I go back to my Excel file. I already asked Excel to report the residuals and even the standardized residuals. What I will do, I said that I would like to plot the residuals against the predicted values, predicted winnings, right? Here they are, the predicted winnings. They are also reported by default in Excel. So I will plot these two. Here you go. This is my so-called diagnostic plot, right? That's my diagnostic plot. And if I do the same now for the log transformation, I draw a plot of these two. Then this is what I see. That's also the diagnostic plot, but this is for the log winnings example. And I compare the two, right, for my two models, right? And I see that in one, I have a clear pattern, right, in the diagnostic plot. And here, I do not have a pattern. The points are completely scattered, and I have a chaotic scatter plot here. And for once, chaos is good. The more scattered the diagnostic plot is, the better. So among these two plots, what I also reproduced here in my slides, the chaotic one is good. This is not good. If you see a pattern, that's not good. It means that the linearity assumption is not satisfied. And why? Why? Because it means that, well, I still see in my residuals a clear model, right? I did not extract all the relationship between y and x. I have a remaining relationship, right? So to summarize, in diagnostic plot, so here we are checking the linearity assumption. So linearity assumption, how do I check it? If I have a clear pattern, right, like on the left, this means that my linearity assumption is not satisfied, right? So here, linearity not satisfied, not okay. And here the linearity assumption is okay. Right. Fine. Now, what else? This is for the linearity, and this I will be able to do even if I have several predictors, several x's. Right? I can always calculate the residuals and plot them against the predicted values. And by the way, whether it's the residuals or standardized residuals, it's the same thing. The scatter plot would be the same. It's just that I would have a different scale here. And finally, last comment is that I cannot have a linear pattern here because the linearity, the linear pattern is already extracted because I fitted a linear relationship. So either it's a chaotic one or a nonlinear pattern that I see. And this means that I still need to look for other transformations because I want to reach this situation in which I do not have a. Now, how about the, so this is how we can do in Excel, what I illustrated. Now, how to check the homoscedasticity assumption? Well, how convenient I can use the same diagnostic plot to check this assumption. And I look this time not for a clear pattern, not a clear relationship, but whether the residuals are increasing or decreasing. Do I have an increase in the variance or a decrease? Well, here I don't see any increase or decrease, so such a diagnostic plot is good actually. So this one I will actually take a snapshot of this one. I think it's nice enough. And here it is. I will report it here. So this time I want to check the homoscedasticity, whether the variance of the error terms is the same, right? So this is for homoscedasticity. Right? And so, right, I use the same diagnostic plot as above, residuals against the predicted winnings, log winnings actually, because we already said that with log winnings we do better. And here, what is good is again chaos. Chaos is good. Here, homoscedasticity is satisfied. And here, imagine that I have this example, which I do not have in the log winnings situation, but imagine that I have something like this. Then this is not okay. It means that the variance is actually increasing. I can even have a decreasing variance. Why not? I can imagine all sorts of situations. So I will plot actually a second one, which is quite the opposite, meaning that the variance is decreasing, right? So here, homoscedasticity is not okay. Okay. Here you go. Now, we were done with homoscedasticity. Let's move to the following assumption, which is independence of the observations. Well, independence actually of the error terms. Well, for this, I will plot the residuals against the observation numbers. If I go back to my Excel sheet, well, we said that I would like to plot the residuals against the observation numbers. So I go down to my residuals, which are here. It's just that they are a little bit hidden by this plot. So I have the residuals here, and I have the observation number 1, 2, 3, etc. So I will plot one against the other one, right? And this is what I see. Well, this is for the winnings case. Here I have a clear pattern. This is actually not good. And if I go back to the case where I have the log winnings, this is the log winnings model, I plot the residuals against the observation numbers, and this is what I have, right? And here again, something chaotic is good. So this is, I will copy it to my slides here. Here we go. So what did I do? I plotted this time the residuals against the observation number, I, against the index, right? So here, we are dealing now with the independence of the error terms. And if it's chaos, if it's scattered, it's good. So scattered means that independence, okay, which we have, right? Now imagine that we have something like here. It's not entirely scattered, right? We see a decrease, right? Here in this example, we see a decreasing pattern, right? A little bit like the variance. The variance here is high and then is decreasing, right? That is clearly, if you look at the index, so the observation number, there is a relationship between these two consecutive observations, right? And also, what is not good, if you see something that is in which you notice a pattern like this, that's not good either. Okay. So here again, if you see a pattern, then it means that independence not okay. All right, here you go. Now, independence done, and finally a last assumption, which is the normality assumption. How can we check the normality assumption? The easiest is to draw a normal QQ plot. QQ plot means it's a quantile plot of the standardized residuals. What does it mean? Standardized residuals is the residuals divided by their standard deviation, sample standard deviation. And the idea is the following. If two distributions are the same, well, the quantize, the distribution quantize are the same, right? And it's true also for the data set. So if two data come from identical distributions, then their sample quantize coincide. So basically, when you draw the quantize of one data set against the quantize of the other data set, or the distribution quantize, then the closer you get, the closer the scatter plot is to the identity line, meaning the relationship y equals x, the better the assumed distribution. So we would like to check whether the residuals, actually we'll do it with the standardized residuals, have a standard normal distribution. So we will plot the quantize of the standardized residuals on the y-axis and the quantize from a standard normal distribution on the x-axis. Concretely, if I go back to my Excel sheet, let's do it with first the first model, the one in which we use the linear relationship between the winnings, and we regress the winnings on the scores. So here, what I will do is that I will actually report here the quantize of a normal distribution. So standard normal quantize. Now, of what? I would like to calculate them for this data. Now, actually, if you think of the data values themselves, if they are ordered, they already if you sort the standardized residuals, they are naturally sample quantized, because the first standardized residual corresponds to 1 over nth, to the 1 over nth quantile, etc. Now, if you look at the very last one, the last observation, it would correspond to the 100% quantile. But what does it really mean if I want to calculate now the standard normal, the 100% quantile of a standard normal distribution? Well, that's infinity, right? I want to avoid this. So what I will do, I will tiny bit shift each probability in my quantile, and I will not consider 1 over n, 2 over n, etc. But I will consider 1 minus 0.5 divided by n. I will shift everybody by 0.5. Concretely, if I go back to my Excel sheet, then here I will calculate the normal quantize. You do it with norms inv, and you specify the probability. And the probability is given in my F column, and we are on row 25. And we said that we shifted by 0.5 and divided by the sample size. Here the sample size is actually 22. We have 22 golf players. So here are my standard normal quantize for some probabilities, right, that we entered. And I will plot them, we said, against the sorted standardized residuals. Standardized residuals are here in this column, and I want to sort them. So I will take these and I will sort them, meaning that I click on data, I press this A through Z button, and I do not expand the selection. I will continue with the current selection. And now I do a scatter plot of my standard normal quantize and of my these are the sample quantize of the standardized residuals. So here it is. This is my so-called QQ plot. QQ plot of standard residuals. And I will do it for my second model. I will do it for the same thing, but for the other model. And I can simply copy and paste my standard normal quantize which are here. I will copy and paste them to my second model here. Here you go. I will copy this column with my standard normal quantized. I will copy them here. And now I draw a scatter plot of my standard normal quantized and standardized residuals, but I need to sort them again in order to form the quantized. If they are sorted, they are naturally sample quantized, and I do not expand the selection. So I plot these against these. Here you go, insert, scatter plot. Here you go. Now, this is also a QQ plot, but for my second model. And if I look at my this scatter plot, I compare the two, right? This one and this one. Well, this one, the second one, is much closer to the identity line. Identity line meaning that is the y equals x equation, right? The one that goes through 0 and 1, 1 and 2, 2, etc., right? This one is much closer to it than is this one, right? I reported these QQ plots here as well, same things. So I can comment on this as well. In addition, I plotted the 45-degree lines, the y equals x equation. And here, what I can say is that this one is much closer, right, to the red line than is this one, right? So we could even calculate the sum of the square deviations from the line for each point, and here it would be much smaller than that here. So we can compare two QQ plots and say immediately which one, in which one the normal assumption is more satisfied. And here clearly on the right it is more satisfied than it is on the left, right? So the closer to the 45-degree line, the better. So this is the normality assumption. Normality of the epsilon i's, and here what I can say is that on the left clearly the normal distribution is not satisfied, right? Even in the middle we have large deviations from the line, right? And look at these large deviations. So we have large deviations actually everywhere, and here we are very close to the standard to the line, right? So here normality okay, and so not okay, sorry, excuse me, not okay, and here normality okay. And so how do I do it? The closer we are, the closer is the QQ plot to the 45-degree line, meaning that it's the y equals x equation, the better the normality assumption, the more accurate the normality assumption. All right, so basically this is what that's all I wanted to tell you. Now these of course naturally extend to multiple predictors. When we have several x's, these assumptions can be checked in the same way. We have tests for each of these assumptions. We have of course complicated statistical tests, more advanced tests. We have only seen visual displays, visual ways of checking whether these assumptions are reasonable or not. Thank you for watching. In case you want to download the dataset or any course material, then this is the link where you can get all this. And well, thanks again for watching.